object here is to discuss the various types of engines. I trust everybody knows what this is. That's the Tesla. And that one you can see in Central Park, I guess, in principle. Uh, so I just wanted to remind people who are obsessed with having one model fit all that the original radio bursts are the solar radio bursts. There's type 1, 2, 3, 4, which come in short and long and moving. And type 5, these two were commonly identified as plasma frequency emission from non-relativistic and mildly relativistic electrons, with the type 4, which are not well understood and they're confusing recent papers, are either gyrosynchrotron or cyclotron masers. So your favorite emission mechanism in your favorite model, some come from coronal mass ejections, some come from bound coronal loops. There are all sorts of different locations, different emission mechanisms, and it's all one engine in some sense, but lots of different places in it and lots of different emissions. So as was mentioned before, there are at least I counted 47 different general types of models that are listed in this convenient theory catalog. So if we start now and spend 1 minute and 20 seconds on each one, we can get through all of them. But perhaps, maybe not all 47 are correct, but 3 or 4 or 5, like the solar radio bursts, might actually be okay. There might be multiple emission mechanisms, and sort of a truism to say in gamma ray bursts, right? When I was a young graduate student, there was one type of gamma ray burst, and now there are 3. There are soft gamma repeaters, short hard bursts, long gamma ray bursts, and all kinds of friends of orphan afterglows, cocoons, dirty fireballs, X-ray flashes, and things which may be related to them. So, there might be one kind of radio burst, but we should maybe be open that there might be a few of them. So I thought I'd start off by trying to narrow the field a little bit. So I think the first proposal for fast radio bursts was Reese, 1977. Roger wrote a paper on the sweeping up of the interstellar medium, and he then sent me off to work with Joe Taylor as a sophomore at Caltech. We did the Arecibo search for fast radio bursts, published in Nature in 1979. I looked back, we did not actually, that was the Holtz-Taylor survey field, of course. We looked for DMs up to 1,280. Unfortunately, we didn't look at the field with the repeater in it. But I think that model is now unfashionable particle physics, so nobody seems to be talking about that anymore. There is dark matter-induced neutron star collapse to black holes and galactic centers. There are many reasons, I think, for ruling that one out, but if anybody wants to argue for that one. There are AGN models of many varieties, but I would say the recent localizations make it look as if maybe not more than a few percent are AGNs. Stellar coronae, well, so does anybody want to? I give this as a problem set in my undergraduate classes. Why the referee should not have accepted that one. But,
tell us how you really feel.
And then I have up here whether anybody really wants to have a meaningful discussion of some of these models, and I found out the answer to this one is yes, so I have Chris's slide next. But if there's anybody who wants to have white hole explosions or alien light sails, we can discuss those. No takers? Okay. So, Chris, do you want to address your slide?
Well, now given me a veneer of respectability. So the motivation for this was the observation, which actually goes back to Reese's paper, that the release of energy, a lot of energy, in a volume smaller than a radio wavelength robustly produces a radio transient. And the black holes have problems, black holes have problems for all sorts of reasons. But there are longstanding ideas of how one could store electromagnetic energy in topological defects. And if you think in terms of ecological principles, there's been a huge amount of thought given to the properties of microscopic particles, weakly charged, millielectric charged, magnetic monopoles cause all sorts of problems. But what about magnetic dipoles? Well, as I said, there's a nice pre-existing model. And this immediately removes the problem of either having a small abundance, very rare object, or extremely long lifetime, because you can rely on the interaction to trigger the release of electromagnetic energy. Now, I should look at my slide to remember what I said. So you can solve the problem of two magnetic dipoles colliding, freely floating in space, and you can populate dark halos with them. And what you find is that the collision rate depends on the ratio of mass to size only, which then can be related to a microphysical energy scale, symmetry breaking scale, which works out to be a ground unified energy scale. So there's a connection between a ground unified energy scale and the rate of apparently non-repeating fast radio bursts, for what that's worth. The mass of these things obviously has to satisfy a certain bound to produce an FRB, but in the model, you find that, in fact, there's a much larger efficiency of radio emission than anything we've been describing today. Not only is there the upboosting of an ambient magnetic field into a superluminal mode, which is what Reese and Roger worked on, there's also a linear conversion of a subluminal pulse produced by the collision between dipoles into a superluminal pulse if the charge particle density is low enough in the pulse. And thirdly, if you reconnect with the external magnetic field, corrugate the surface of the pulse, then there's a standing electromagnetic mode set up around it, and which can propagate away. And all of these three things are basically fairly straightforward linear processes. So there's no doubt that, that you're getting some type of short duration radio transient out. Now, the next thing you can ask is, well, this is very relevant for the localizations by ASCAP and also by CHIME. What's the distribution around galactic halos? Well, if you have binary collisions between dark matter particles, then you can easily work out from the NFW profile what the mean radius of the emitted pulse would be, and it's 1/3 the scale radius, which for a massive galaxy would be about 4 or 5 kiloparsecs. So fine, you can get non-repeating pulses out. These are basically small-scale catastrophic events. But how do you get repetitions? Well, I will refer you to local experts here, those of you who are from New York, who work on the formation of supermassive black holes for much more learned explanation of this. But basically, there is a growing interest in the idea that supermassive black holes grow by the rapid accumulation of gas in high redshift dwarf galaxies. Exactly how that converts to a black hole isn't important here. The important thing is that the mass grows adiabatically. It gathers dark matter around it. People who study WIMPs have made use of this effect to enhance annihilation rates. Here, the particle is much more dissipative, so it settles toward the black hole if the black hole is accreting gas at a moderate rate. And that means then that you can expect, following a burst of accretion, either from a radially inefficient accretion flow or from a tidal disruption of a star, there to be a tail of annihilations lasting 10 to the 4, 10 to the 6 years. And the important thing here is that these black holes, if they are forming high redshift dwarfs, quiescently, will be inherited in a significant number by a massive galaxy like the Milky Way. Tom Quinn's group has done simulations of this, and one lucky black hole gets to the center of the final galaxy, and then the remaining ones are circulating around within 5 to 10 kiloparsecs from the center. So a supermassive black hole that is situated near the center of a galaxy or in a dense bunch of gas would be expected to have a large rotation measure, but the ones circulating around in the halo would not necessarily. Okay, and so so that is one point here. Now, finally, how on earth do you get something like the clusters of bursts from 121102? I mean, the intrinsic annihilation rate in this model can't be anything that high, I don't think. But there is a prior here, which is that if you're emitting radio pulses from close to a black hole, the accretion rate has to be below a critical value for the radio pulses to escape. The electron density has to be below a critical value. And the intense radio pulse helps the escape. That was taken into account. There's some suppression of synchrotron absorption, for example. But that means, though, is because of the low accretion rate, any disk around the black hole will have frozen out and basically formed a thin quiescent structure, which in fact, something like that may have been seen around Sagittarius star. Now, there are simulations by Price's group, for example, showing how such a disk near the boundary of effectiveness of lens tearing, about the competition between the lens tearing torque and the self-gravitational torque, would cause the disk to fragment into rings. And perhaps that would also be clouds. But anyway, there's a real prospect then of having some reflection surfaces situated at about 10 to 3, 10 to 4 gravitational radii, with an orbital period, although they never bothered to work it out, of 10 to 100 days. Whether that really works in detail, I can't tell you, but it's plausible that you could get a 10 millisecond burst duration, taking into account the differential time delay of rays across, reflected from the surface of a curved plasma sheet.
I guess, Chris, can I ask a question?
Yeah.
It seems to me that you have, the range of delay times and sort of complications in the burst is sort of ranging, as near as I can tell, sort of uniformly between tens of milliseconds, minutes, hours, days. You can get sort of different timescales from different mechanisms. Do you think it's actually sort of having a continuous distribution across all those timescales as for a single object? I mean, for like the repeater?
To be determined. Certainly you're starting, I should emphasize in this model, with a very, very narrow pulse of the order of a few wave periods.
Sure. So even a few wave?
Even starting with a few wave periods.
Yeah,
yes.
okay. I think that's very, very interesting, Chris. I mean, you said that delta T is 1 to 10 milliseconds.
Yes.
But that's for the reflection.
Reflection. So
Yes.
H here is the scale height.
You're starting with
thermal
something,
scale
yes.
height. Yes.
But it seems to me that is a killer observation for a large class of models. If you can, we've heard here today, I think 40 microseconds and so on. And if everything is consistent with, essentially, very short durations like that, then
I don't mind short bursts.
Yeah.
It's the longer bursts which, involve more complicated physics.
So I guess maybe this is a question for the
Yes.
observers. Is honestly considering propagation and scattering, is it? I mean, I guess if there's a prediction of 10 nanosecond bursts at 400 megahertz, are nanosecond at gigahertz frequencies, is that something that would be possible to actually measure?
As long as scattering doesn't.
Right. Well, that's the question: is whether scattering and uncertainties in DM and stuff.
Yeah, you need to get but I guess this was back to the morning when we talked about the killer, observation, right? So if you could find a pulse that was,
Well, one interesting future, direction which I was just hinting at this morning is looking at much higher frequencies, right? Where, it's possible that astrophysical sources, are rising in nu F nu with frequency, but it's not obvious. In this case, it's flat or rising, okay? So microwave background experiments should be seeing bursts. And you're getting close then to actually resolving the physical size of the emitter at those frequencies.
So that sounds like the Owens Valley should stare at the repeater at 30 gigahertz or something and look for tenth of a nanosecond pulses.
I mean, if you can rule out essentially delta function initial pulses, that would be a step forward. But it wouldn't necessarily stop Chris because, going back to Rudin's analysis of gamma ray bursts in the 1970s, every model posed could be correct for one burst. And, so in sort of limits, as Stowe was trying to say. And so, you could still be only right for a class of them, but it could be an important class,
Well, just two final comments before. I wrote a paper showing calculating the effects of gravitational lensing, because you're emitting close to a black hole. It's a nice, pretty little problem. The continuous emitter had been done for a long time, but the delta function impulse, all sorts of pretty patterns on the sky and ringing effects and so on. But there is an observational bias. If I have a repeating source and it's next to a gravitationally lensing object, then there is a observational bias in favor of the observer sitting in the plane of of the orbiting emitting particles. And so here, trying to fit this to 12.11.2, I claimed there was some evidence for about a factor of 10 increase in flux due to gravitational lensing. And the last thing is that you can calculate just from the v cross b acceleration of the electromagnetic pulse, the very simple v cross b acceleration, what the limiting energy of an ion sweeping across the pulse is. And that is related again to the ratio of mass to size, therefore to the symmetry breaking scale. And for a gut scale, it's 10 to the 19 electron volts for protons and a few times 10 to the 20 for iron, which I never expected and was rather pleased at. So I'll shut up at that point.
Yeah.
Ryan, did you want to?
Yeah, I guess, yeah, I'd comment on this, and then it's also, I was talking to some string friends last week, and I think one interesting point is that we've found a few FRBs that have come from disks of galaxies, so not from like halos of galaxies. So I think with those ones, it's less probable that you're tracing sort of dark matter or things like that. So that's kind of interesting.
So in the sense, if it's
It's off-center. It's off-center.
yeah, they're all
in
center.
spiral arms. I don't think the dark matter would necessarily, something that's tracing dark matter.
I guess so. Are they the pictures that are shown? They're mostly face on. If you, I mean, I guess it would be most compelling if it was edge on and clearly in the disk as opposed to above it.
And I think Ryan, the point's that even it's face on, you can still.
Yeah, it's still consistent with the star forming region. I
Yeah.
agree. Yeah, Vicky.
Perhaps I didn't quite understand, but are you saying there's supermassive black holes circulating around galaxies, and could there be in the Milky Way?
That's a clear implication of this formation channel for supermassive black holes, which I had nothing to do with. It's a pre-existing piece of.
Oh, I didn't really realize that. So should we not see evidence of that in our galaxy? Or?
Well, the best way of finding it is probably through TDEs, because low mass supermassive black holes tend to be associated with nuclear star clusters. And even if the host dwarf galaxy were tidally disrupted during assembly, it would carry around the nuclear star cluster with it.
So just to clarify, these are like 10 to the 4, 10 to the 5
Yeah,
solar
these-
masses
these
and
are
below, not
tiny.
10 to the 9.
Pretty
So
massive black
yeah,
holes, right?
yeah.
Massive super. Yeah.
They tend to have higher redshift, right? Not the current, right?
Which
No, there should still be. No, there should still be in the. There's still predicted to be over 15 or something in the Milky Way. Yeah.
Tom Quinn's group, as I said, has done nice simulations of this.
In the Milky Way.
Yeah, I mean, in the halo, they come in at a lower and lower rate as time goes on, but I mean, they're started off with thousands of merged, but there's still dozens or something circulating.
But the bond accretion rates are like, when you take into account the inflow-outflow effect, like Roger and Begelman worked on, it's like the bond accretion rate that makes it all the way to the black hole is likely to be quite small.
But you see the nuclear star clusters then?
You could.
Good,
Yeah,
yeah.
so that was
there's an
Peter Jonker has a
application
Gaia proposal to look for
all people
those.
localizing FRBs and halos to try and see if you can find any nuclear star clusters.
Yeah, I think good idea. And just to make it absolutely clear, the idea that dark matter is all sort of million solar mass black holes, was posited and taken seriously some time ago, but it's now completely impossible.
Yeah.
But the idea that there's a significant fraction of the density is in this form, or an observable fraction of the density, you don't have constraints on that, and so it's worth looking in that regard. Yeah.
So what's the inspired timescale for these in the galactic potential?
From 10 kiloparsecs, it's infinite.
It's infinite.
I mean, they're like globular clusters. They're the same mass as globular clusters.
With a million solar masses or more, but less than that, it's there forever.
Yeah, they're the same mass as globular clusters, so the globular clusters are still there, so the black holes should be too.
No TDEs.
Yeah, TDEs and Peter Jonker had this proposal to look for the little star clusters around them because they're 1/10 of an arc-second resolution, as well as the TDEs. But, yeah. Okay, so to me, I guess this is sort of an important question, which I think has been asked a lot. As time continues to observe, how does the repeating fraction evolve with time, right? And one would expect that if all FRBs repeat, then that fraction should increase with time. So there were lots of one-time models which have been proposed. I don't know whether we want to go through them. Some of them have been discussed already. The rate question was kind of raised. So So I think, there's the 600 per sky per day at 1 Jansky at 1 gigahertz. My estimate is that chime is actually well above that, but of course it's at lower frequency. And so I think the rates are something like at least 1,000 per sky per day, depending on how you extrapolate with flux and frequency. And so the LIGO neutron star black hole rates, if you run certain by a factor of 3, I think that's sort of a median value, is something like 130 per sky per day, which I think is telling you that the majority of these are probably not one-time events. And as has been mentioned, the core collapse supernovae is something like 10 to the 5 per sky per day, so you have plenty of room, at least till the FRBs get down to really low fluxes. Yeah.
These are detection rates for LIGO, which is a different thing than.
This is the inferred rate per cubic gigaparsec per year in the local universe. Then depending on what redshift. So this is redshift to 1. If you just, the FRBs are typically more like 0.5, so maybe it's even less than this for volume. And this is the local supernova rate. If you actually go out to redshift 1, of course, it's evolved up a little bit, but I mean,
The error bar on that.
the error bar on the core collapse supernovae rate is pretty good. The error bar on this is a factor of 3 either way, I think, at the moment. Yeah, I mean, they're now 3 events you might want to put in there, so the Poisson statistics are not quite so bad. But yeah.
I think maybe what Jana was getting at is that we now have measured neutron star merger rates from LIGO, and then there were also the predicted ones.
No, this is the measured and the
Making sure that
that's measured with the current Poisson and other uncertainties.
It has to do also with LIGO's inability to see here very faint.
This is from the 3 detections. This is the actual claimed rate from the LIGO papers. Yeah.
Yeah, I actually think it's really difficult to relate the sky per day rates to volumetric rates because of incompleteness effects.
But I think it's a lower limit, right? I mean, the fact that most FRBs that are dominating the rate are probably not at a redshift of 1. These are, I don't know, chime is, given chime's field of view, is something like it must be at least 2,000 per sky per day. And so maybe, if you took this as a redshift of a half, this is 30, right? It can only be worse than this. It can't be better, I think.
True, but I guess what I mean is, for example, comparing it to the core collapse rate, that as you go further out in DM, your volumetric rate estimate just starts to drop significantly.
No, as I said, this is the local one. So, at a redshift of 1, you'd boost this by a factor of 3 or something. Is that what you're...
Quite. I'm sort of saying that that the difference between the 10 to the 3 per sky per day and the 10 to the 5 could be.
Oh yeah, I'm not saying
at redshift 1, right?
This was not to say that every supernova couldn't do this. It's more about the one-time events. This comparison. Sure. This could easily be 10 to the 5 per day at a redshift of 1. I think we don't know. It was this direction that I was emphasizing, not the other way. Yeah. So I guess I just wanted to see if there is a significant loophole in this. Is there anybody still thinking that the majority of FRBs are from one-time, say, neutron star black hole blitzar type models, or can we declare that one finished?
I said yes.
Could be a couple of them.
Yes. I think yes, right?
Yeah, I mean, I think it's
One
like
time
you presented in the beginning.
Yeah, I mean, it's obviously fine for 1 out of 100 or 2 out of 100 or something, but it was just as for the typical one, I think.
I'd be really excited if 2 out of 100 were observed and confirmed with some kind of smoking gun. I mean, it'd be less happy for y'all, I suppose, if you want to explain all the FRBs, but I think it'd be pretty exciting.
I guess I would just say that I think the thing to do is to get on a LIGO source with a radio telescope, and I think going the other way is probably more fruitful.
Yeah, so I mean, we'll come back to that. I mean, obviously, I think there are lots of ways. I mean, these one-time ones, of course, it's not hard to take one of these mergers and do things just before and just after, make a magnetar out of the merger or have interaction before the merger, and then you can get multiple bursts out of each one. So that, I mean, I think the same engine, in a sense, can have lots of repetitions with slight modifications. So I just wanted to bring this up again. When I was young, I went to a conference on the a whole conference on the March the 5th, 1979 gamma ray burst that was the prototypical gamma ray burst, and it constrained all models of gamma ray bursts and determined the models. And we now know that that was an SGR in the Large Magellanic Cloud. 1806 minus 20, that was 10 to the 46 burst. It was pretty impressive. Changed radio emission in the Earth's atmosphere. But that was also a magnetar, and of course, those were not the prototypical gamma ray bursts, which are from other types of sources. So I guess the question is the original Arecibo repeater a similar red herring, just like the March the 5th, 1979 burst? And lots of models were immediately tuned to explain this, and the question is, have they maybe been overtuned, or has it unduly influenced our impression of what the typical FRB is? So I'm still confused now about whether FRBs are or not in star-forming galaxies. I think it seems to be evolving.
They are for sure. They're both. They're in any type of galaxy you know about.
Okay, so they're not all in star forming, and they're not all not in star forming is acceptable. Okay, so we're making progress here. Good.
I mean, I would push back on this a little. Not to say that this isn't, this can certainly be possible. This could be a red herring, but I think that the fact that some of the other bursts show different characteristics is not necessarily in tension with the models that were built for 121102. So as one example, the rotation measure, I mentioned in my talk that you can turn the dial.
You can wait 100 years
by a factor of a few, and then you can get significant decreases in rotation measure in persistent sources. So it's very easy to evade those types.
Can you turn your microphone on, please?
I see. Sorry. So again, I think the fact that we have lower rotation measures for most sources and only upper limits on other persistent sources at the moment is constraining, but certainly within the lines of what we might predict within the model that was tuned for 121102. So when in our 2018 paper we sort of speculated that if the magnetar activity or the engine activity decreases as some shallow power law with time, then you'd expect sort of a logarithmic distribution in rotation measures. So it's equally likely to find a 10 to the 5 as it is a 10 rad per meter squared rotation measures. Now, obviously, we don't have any more 10 to the 5 ones, but there are observational biases against that.
But for example, if we consider the ones in elliptical galaxies, fine, you can do it with accretion-induced collapse, but the evidence for accretion-induced collapse in globular cluster is 10 to the 8th Gauss, 10 to the 9 Gauss, or I guess more like 10 to the 9 Gauss pulsars, and does the amount of gas in the surrounding medium or the magnetic field have any effect on these models?
So in terms of you're thinking about the localizations themselves, so I think the emerging evidence is that most are in star-forming regions. Now, they do span a range of galaxies.
There's some in ellipticals,
yeah,
so
that's true. And you can make them
for those.
So I mean, as we've argued, you can make them through AIC or by other means, but certainly there are many caveats and open question marks to do with that.
And I want to point back just from a purely observational standpoint. I mean, the repeater shows this sad trombone behavior, which is seen also by 9 out of 10 or whatever time repeaters. So I think there are some aspects, at least when you get to the intrinsic properties of the burst, which are suggesting that they're not. I don't think we're yet at the stage where we have 5 classes still. That's what I'm saying.
I think it's quite obvious that 121102 is the same type of source, the same engine as the other repeaters. Otherwise, you wouldn't see that very characteristic.
So you said the other repeaters?
The other repeaters,
yes. But would you make a stronger statement that there's nothing
to
distinguish it from all of them?
But I guess we've heard.
I'm not sure how many of the apparently non-repeating ones also show the same drifting. Of course, the 121102 doesn't always show that drifting either. So.
And what about the statement that the repeaters are broader? I guess is that a time-independent statement? The durations were, I thought, in your history.
Breadth of the pulse.
No, so
Specifically, it is the 12.
well, no, but 6 months ago, when Chime didn't have so many repeaters, in the histogram you showed all the non-repeaters had short
And there were
bursts, and
only
all the
12.
repeaters had long ones. But some of those weren't repeaters 6 months ago.
Yeah, I understand what you're asking. I'm not answering it, but I understand. I don't know.
The most striking thing personally found that this Laura's talk, where she emphasized this for the first repeater, the constant in time, the polarization position angle is constant, whereas we see from Ryan's talk there's a counterexample, very striking counterexample. So that's clearly indicating, it's very constraining, clearly indicating the first repeater is very special, kind of special maybe. I find that's very dramatic, this example. These two contrasting example in these two. For me, it's very constraining because it's very hard to make the thing constant over many years. It seems to be you need a very stable configuration.
Yeah.
On the topic of the RM distributions of FRBs, it's not as if there's one with 10 to the 5 and then the rest are consistent with the Milky Way foreground plus the IGM. The ones that are 100 or 500 or 200, like the GBT one, are inconsistent with the IGM and the Milky Way foreground, and they're very atypical. If you observed a pulsar in the Milky Way from a random angle, it wouldn't have an RM of 500 unless it were in a special place. So.
Oh, I think Ailey had his hand up for a while. Yeah.
I think one of the issues is that we know that the age of the special repeater is the age of the system is rather short. So it's about 100 years old, and this is a very short time. So, what? Yeah. So it could be that it is maybe special because it is much younger than the others. It depends on the lifetime of the sources, and we don't know.
But on the other hand, there seems to be one strong prediction of if it really is 30 or 100 years and the others are 300, it should be evolving.
Should be evolving
properties rapidly. Which
Well, but all of those are, consistent. So the predictions of those models are consistent
just over
with
the next decade.
Yeah,
if nothing happens in the next decade.
So in 20 to 30 years, 20 to 30 years, we should be able
Ask me again in 20 years.
Yeah, Jason.
Yeah, so I was just going to push back a bit on the polarimetric properties argument, because I think, the crab shows a variety of different pulse components at different frequencies, main pulse, interpulse, that have characteristic polarization properties that are quite distinct from each other, but they're obviously all coming from the crab pulsars. So I think if one FRB looks different than another FRB in terms of a swing or whatnot, it doesn't mean they're different types of objects necessarily.
So we haven't yet got this end of the panel involved. I don't know if you guys have anything you want to opine about.
So I have your.
Please step in if you do.
Yeah, I have Bing's slide coming up in a minute. So, so I guess this was sort of related to the the question of locations of magnetars in new places from the point that Ben made. Maybe age and EDT give enough parameters in the magnetar model that one can fix the RM and persistent radioluminosity distribution. Then in the outskirts, it seemed to me one needed a somewhat different origin for the engine, at least probably with different properties of accretion-induced collapse or mergers of objects. I don't know whether is Jim around to talk about comet and asteroid accretion?
It's possible.
Not yet antimatter comets, but just regular ones. Yeah.
I have to say that when Ruderman gave this talk on the RBs, he also said, for those of you who want a new option, there aren't many left, but comets of antimatter falling onto white holes. It's still a possibility.
Yeah. Just two. One comment is just too expensive. You don't have so many rockets. Comets to fall onto neutron stars because thousands of them in 1 month. Too many.
Well, I don't know, Jim. You want to is that a problem? And I was sort of struck in Andre's talk. As the repetition intervals getting short repetition intervals seem to me sort of constrain. We talk about engines, but magnetars can either be. You can imagine. There've been papers proposing emission from near the surface of the neutron star all the way out to 10 to the 14, 10 to the 17 centimeters, and maybe we can try to constrain at least the difference between the, whether it's RFI from the generator or RFI from a radio a long way away.
Could I try a question there for those who want to make the emission from out in the wind with shock waves and so on, and
if it were shown that the intrinsic durations of the pulses were short, microseconds or so, or less even, would that be an extreme difficulty for doing things from a wind? Because you had sort of delta T of order gamma squared r and so on. You have to do the no.
You can just push the button.
No, sit where you are. And
Just push the button.
You have a button. Yeah, you should be down here. Yeah, you should be down. Come.
Is it better? Okay. Right. So I have my own here, so that's I'm okay. The compression time, compression factor, gamma square factor, the compression is so huge for these blast waves. The shock Lorentz factor propagating through the wind is 10 to the 5. So actually, by default model, if you don't try to adjust the model to the data, but just calculate what you would expect, the typical duration of the blast wave emission would be less than 1 millisecond. It would be maybe 100 microseconds, maybe even 10 microseconds, which, yeah. So I actually view it as a potential problem, but it's not clear that maybe.
But I guess is it fair that nanosecond would be a problem?
Nanosecond would be, I guess, yeah.
So that would be in favor.
Well,
of
a related question, Andre. Your talk started speeding up toward the end. I was beginning to get lost, and but in essence, you are positing that the magnetar wind has some cold positrons and electrons in it.
Yeah.
Now, we know some magnetars are sources of coherent radio emission, pulsars. And there's long-standing argument that you need the electrons and positrons in a pulsar wind to be relativistic for the radio pulses to escape. Wilson and Rees, I think it was Wilson.
Yeah, that's right.
Yeah.
And so that's a constraint.
Yep.
But also, it seems like a fragile thing to me that, you've got this, still most of the energy coming out in the magnetic field, and you have to keep things very gentle before the shock comes from below, associated with a really big flare. And we know that associated with magnetar flares, there are all sorts of much shorter bursts, right? There's, very well yourself, there are clusters of a wide spectrum of energies. And so,
Yeah. So the explosion probes only a small fraction of the wind that was emitted just before. The main giant flare went off, and so we are probing the last maybe second or so, or the second just preceding the explosion. And indeed, the wind is not the quiet wind that you would expect from normally rotating magnet. It's probably changed by. It's not changed by the activity that you had days or weeks before that, but just the last seconds before the main giant flare.
Well, I think the best way to say it is that, right before a magnetar flare, we really don't know what's going on, right?
And I completely agree with
that.
And
it may be there's a period of quiescence and then kaboom, but it could be a gradually rising chorus of larger and larger activity, right?
It could be. But we also see that before main giant flare, from the simulations, we know that the magnetosphere has to inflate. Right. So you probably would expect that the wind will be stronger than normal spin down wind for sure. But by which factor, we don't know. And how much more pairs you load in the wind, we don't really know. So within a 1 or 2 orders of magnitude, there's a huge uncertainty.
But I guess, Chris, was your concern whether the electrons would actually be cold all the way out, basically?
Yeah, but they should be cold. This I didn't get. Why they should not be?
Can I try and say that I think what Chris is saying, and this is not, it can still work, but I have to say that large bulk Lorentz factors in what are essentially hydrodynamical or gas dynamical environments have always frightened me, because it's essentially a Mach number. And if you imagine doing gas dynamics in a some nozzle or something like that in a laboratory, it's really hard to make large Mach numbers.
And that's why SS433 is impossible, right?
Yeah, for example, yes, it doesn't exist. Yeah, but it is a challenge, I think, to make these large Mach numbers. As Chris said, you have to be rather carefully prepared ahead of time.
If you have very low baryon loading, then why? If you in vacuum you have infinite almost Mach number. Yeah.
It depends whether it's essentially gas dynamical or essentially electromagnetic or essentially vacuum? It's the first one that I think is the worry.
It's there's so much space between the vacuum regime and hydrodynamic regime when you don't have inertias, but you do have enough charges to screen out the fields. And I think this is the regime of the main, when you eject a chunk of magnetic energy, you don't have much inertia in the plasma, but it's still force-free. And it does develop huge Lorentz factors.
So just on these large Lorentz factors, can you say a little bit about the actual beaming angle of the emission and whether you expect it to be smaller or larger than 1 over gamma?
It's big. It's not. When you imagine a flare happening in the magnetosphere, once it begins to leave, it expands in all directions, more or less.
Yeah. Okay.
And so it's not strongly beamed.
Okay. So superluminal motion is possible then.
Yeah. I mean, the other thing, of course, is it's a bit like the expanding universe and so on. If you've got a large angle of emission and locally tiny 1 over gamma beams, then these have all got to talk to one another, and so it's like the problem of inflation cure.
Maybe I can try to connect what we heard this morning. I was struck by Vicky's talk, where you mentioned that within a given source, the different pulses have wide range, a diverse range of duration, right? And so I was wondering, for example, your model or other models, whether the theory have, in your case, the duration, in Andrew's case, the duration is set by the distance and the gamma, both of which are well constrained apparently, based on physics. Do you have enough flexibility to accommodate this kind of diverse range of pulse widths?
Not really.
Not really.
Yeah.
So I mean, it seems to me this is kind of thing maybe can be useful.
The big
other model.
Well, you both can. You can.
To a certain extent, yes. So that I was showing the.
Very constraining.
But the inferences would be similar in the sense that the inferences in Andre's model, I believe, would be similar in the sense that the timescales, the durations are still r over gamma squared, and to get the energy right and the frequency right, you still have these other constraints on gamma and r. And so I think you do have some flexibility. I mean, I showed the model applied to observations, and it does work for observations. But in the extremes, of course, there are difficulties. So, for example, I don't remember if it was one of the ASCAP bursts or Vikram, your DSA 10 burst that was extremely narrow. And if you looked at that plot, it was also very energetic. But on that plot, the implied Lorentz factor was much higher than the other typical chime bursts or SIBO bursts. So you can accommodate it, but you need somewhat more extreme parameters. But of course, there are subtleties where you can complicate things, right? You can talk about things like resonances from the synchrotron maser passing through your bandwidth, and that setting the temporal timescale or other variations thereof. So this is just the naive sort of vanilla model.
Of course, the big unknown is the propagation effect, right? So do we really believe that this millisecond or sub-millisecond duration is that you observe it's intrinsic?
I see. So the duration that
yeah.
may be intrinsic.
Let's see, Harish, did you want to?
Like in this model, every FRB should be preceded by the ejection of a shell, right? You said.
No, it's likely that, as Ben also would tell you, that if you think that the nebula is made of electron ion plasma, then you do expect electron ion ejection, relatively slow injection, to be polluting the wind now and then. But I think that running an explosion into quasi-static medium is problematic for producing an FRB, and so it would run into relativistic wind of pairs, which is supposed to be cold.
So you don't run into any mass problem, having like thousands or millions of FRBs.
No, I think the FRB itself is produced by blast waves in the quasi-persistent but maybe enhanced electron positron spin-down wind from the star, which is always there. It could be enhanced before the explosion, but it's always flowing from Newton's star, and it's not polluted dramatically with ions. There is some ejections of ions. As we know, magnetar flares do eject ions. We saw ion ejection in one of the giant.
That's not necessary for the relativistic shock to ram into.
But it's not. No, I think it actually would kill an FRB if you. This is now biggest.
So yeah,
I mean,
there are two
debate.
variations. I think I tried to mentioned this a bit in my talk, but there are two variations to these blast wave models, at least two. And the major two differences are what is the nature of this upstream medium that the shock runs into. In one case is you run into this ion shell, which I think is what you're asking about, and then in another scenario, which Andre has been talking about, you run into a pulsar wind nebula. But to your question about the mass problem, even in our scenario where the upstream is...
Not nebula. Not nebula.
Sorry, pulsar wind.
My understanding was to get the emission again at the same frequency, you need a fresh shell, because otherwise the relativistic shock moves into the shell and you won't get the emission at exactly the same frequency in the next burst.
So again, in our scenario, you run into, well, you have two options. Either you run into a fresh shell of ejected ions, or you overtake basically the previous shock. You have a more energetic shock that overtakes the previous one.
Okay, so that was my question. In the fresh shell scenario, how many FR bursts before you run out of mass to eject from the neutron star?
Oh, for a given shell, how many bursts before you run out of mass?
Yeah, let's assume one fresh baryonic shell per FRB. Like when
well,
you run out of mass.
Yeah, we haven't gone through that estimate. I mean, it would be easy to do. But
the individual FRB doesn't get very far.
Yeah, it doesn't propagate. I mean, because the medium is so dense ahead, you really don't propagate very far. So I guess the two options are either you have something that's slightly, that overtakes it, or something that doesn't and doesn't produce an FRB.
Just to come back to this point about the widths that Dong brought up. So first I wanted to try and pin you down about intrinsically what diversity in widths could you see, and then about propagation. If the majority, I guess I don't know why propagation effects always give you a sad trombone as opposed to a happy trombone. And so because we see a preference for sad ones, that suggests it's not propagation dominated.
So I guess, yeah, and the question is, I guess, what do you mean by propagation? So I think there's some models where you have scattering doing this sad trombone, but I think someone like Jim would be, could comment on that better. If in our scenario, it's really the emission itself, the mechanism itself that produces the radiation that creates a preference for a sad trombone. So it's not propagation.
Sad trombones, my understanding, they appear when one tries to maximize the amount of structure in the burst. Is that right? I mean, there's obviously, you could turn a sad trombone into a happy trombone with a different DM, but then you wouldn't have these sharp features. And is there any other?
So I think yeah, Ziggy should answer this.
I think that's right. If you look at the data, however you de-disperse and move it around, it's impossible because the emission stays in the same frequency channel, so you cannot push emission at the bottom right over to make it happy and drift upward. However you shift it.
But you could move it earlier, couldn't you? I mean, just moving it horizontally.
Yeah, I guess then you would have I'm not sure if you would call that it's a different. Then you would have something that sweeps upward like this,
right.
And it comes. Yeah, if you would call that a happy trombone, then that would be
happy trombone sweeping up.
So I think part of the argument is that you would then have radical changes in dispersion measure between bursts as a function of time, and so sort of the minimal argument is that you want to you have assumed the electron column.
So I guess is it true that if you pick one that maximizes structure, exactly the same DM maximizes structure in all subsequent repetitions? Okay, so that's a useful. Okay. Yeah.
The other argument for that is that a dispersive medium will actually lose information in a pulse, right? And so if you want to maximize the amount of information in the pulse, that should get you should be getting rid of all the dispersion. So by having structure in the time profile, the integrated time profile, you're basically increasing the amount of information that was there at the beginning before it entered the dispersive medium.
Right, but I mean, a counterexample would be I could start with the Gaussian pulse, and by shifting pieces around, I could make it spiky.
I don't think you can.
But I could make it one spike. I guess what's not clear to me that I can make four. That I agree with. So, yeah. No.
I have a question for Andre. Oh, he left. And now for Ben. Yeah. So in the relativistic shock scenario, the observer doesn't see a one-dimensional shock. It's a spherical, quasi-spherical shock. So you see actually all the emitting area within 1 over gamma that you see. And the edge of 1 over gamma cone would have a compared to the center, this frequency is shifted and arrival time also shifted. So accounting for this equal arrival time surface, you would see delta nu over nu of order unity. Right? I don't see how you can get like narrow band, like if there's intrinsic, of course there could be propagation effects, but how can you explain the narrow frequency or narrow time structures?
Yeah, so with respect to the narrow frequency problem, any model that has relativistic, right, relativistic bulk Lorentz factor has an issue with producing very narrow features in frequency space. That's, I think, a generic problem.
I mean, to be the devil's advocate here, because I'm not so sure I believe that in the Maser models, but I mean, it could be, one thing that used to be said was that you would get frequency structure for Masers simply because along certain directions, because of the peculiarities of an inhomogeneous medium, you just get different gain.
Yes.
So you would be rather spiky in frequency. I mean, this is one of the things that was generically said.
But you're looking at different area on the let's say emitting spot. Then you average.
So
yeah, you average out.
I understand, but you may only be looking. I mean,
I'm
not a defender of this. You may be dominated by one or two beams
yes.
at any time.
Yes.
With a large, and they could be, localized
smaller
in
over again,
also in frequency.
Yes.
Total case space.
Okay.
I think Lorenzo had something to say too.
I'll give you part of the answer that Andre might have given, which is that if you're thinking about this scenario, the shock-dominated Maser scenario in a high sigma medium, the shock is actually moving ultra-relativistically with respect to the post-shock at square root of sigma. So the Maser is actually even more beamed than 1 over gamma because you're only carrying away in the upstream the waves that actually can make it. And the shock is moving so fast with respect to the post-shock that you're actually constraining significantly the opening cone of the emission. So it's much more than 1 over gamma if gamma is the post-shock Lorentz factor.
No, here's Andre back. You can see if you got it right. Yeah.
So, in the magnetar models, the pre-flare wind where the blast wave moves into should be in some sense modulated by the spin of the magnetar. And why is that not easily observed in the pulses, the FRB bursts?
Sorry, I'm not sure I followed. So why is not easily observed?
So in the magnetar, so the pre-flare wind where the blast propagates into would be modulated by the spin of the magnetar. And why, if that is the case, then it should be compressed within a millisecond duration. And why is that not easily observed in the bursts?
Yeah, so there are a couple effects that the magnetar, the spin down powered wind could have on the environment, or spin in general. One probably important effect is just setting a preferred direction for magnetic field at larger scales. And so you imagine that the baryonic shell that you eject from these very strong flares that the shocks later run into, they have to have some large-scale coherent magnetic field to set a preferred direction for the Maser. And so you imagine that if the ejection of these flares occurs over timescales that are longer than the spin period, then for example, second timescales or so, then you can sort of wrap the magnetic field into these shells. So that's one effect that the wind can have. A second effect, which I think Andre mentioned a little bit, is that you can sort of sweep up the shell. So you can basically, depending on the spin down power at any given moment in time, you can inflate a bubble. So this wind can sort of sweep up the tail of the ion shell that was previously ejected. And so that crucially depends on what you assume for the spin down power. And you could have, some region where you basically pile up, a shell of shocked pairs at the tail end of the ion shell.
Could I ask the magnetarians if you really envisage a 5-second period as you observe in the boring ones in our neighborhood, or a millisecond period as you might even envisage for a freshly graded one? I mean, is it crucial, the answer to that question, or not?
No, so for us, it's not crucial. We don't need fast rotation. We don't need millisecond periods.
guess can I ask another question? So presumably, if the magnetar's magnetic axis is not aligned with the spin, there will be some region of striped wind and some region of not striped. Does one expect different FRB polarization or any other behavior in the striped wind versus the non-striped wind?
Maybe Yuri can comment since he's going to talk about this stuff.
But I think millisecond period exists only a few seconds. So already after 10 years, period of magnetar is already good fraction of the second. Therefore, no sense to discuss millisecond magnetar because it is still within the star or within the very dense envelope.
I guess I was asking because Sterl was asking if you'd expect any difference in the FRBs you would see in the equatorial plane where you have the striped wind versus not. So
well,
I know you're going to speak about
in model I am going to discuss tomorrow. Yes, but
okay. So so maybe.
Okay, so the answer is yes.
Yes, possibly.
So I don't know, as we've covered some of this, I don't know whether you wanted to address anything in your slide or Ben wanted to push back. Yes.
Should I go through these one by one? Yeah, you know.
So I think there are a couple. I'll take maybe the first two. So let me start from the second one. We should have detected FRBs or should detect FRBs from these remnants. Yeah, to some extent, yes, at least from some of them. I think that the amount of time that's been spent so far of order an hour per source, and so I think it's far from constraining of saying yes or no. So I wouldn't take that as just...
everyone is as active as 12.11.02, then probably we should already see that. But maybe if within...
I think for 12.11.02, I don't remember exactly what the number is, but I thought it was of order 100 hours of VLA time before one burst was detected. So I think we're a couple of orders of magnitude away from that. So I wouldn't take that as a hit against... I think the time should be spent. It's very hard to convince time allocation committees to give us 1,000 hours for this kind of search. On the first one, again, you're saying most are in old environments. It seems to me like that's not the case, at least from what we heard today. Maybe the more correct statement is most are in more massive galaxies than superluminous supernova and long GRBs. The other thing I would point out in terms of specifically the superluminous supernova is in the context of explaining those events as being powered by magnetars, those select a very specific set of properties. So of order a millisecond or a few millisecond rotation and of order 10 to the 14 or 10 to the 15 Gauss field to really give you a boost in luminosity in the optical compared to a normal radioactively powered supernova. If you just dial those numbers down a little bit, if you get a 10 millisecond rotation magnetar or a somewhat weaker field, then actually those could be created in normal core collapse supernovae and we wouldn't know.
Or even a higher magnetic field.
Or higher magnetic field, yeah, to spin it down more rapidly. So 10 to the 16.
Yeah.
And so I think what we're seeing as the phenomenology of superluminous supernovae is a certain slice of properties of magnetars, and it's possible that the other ones are just not appearing. And so I wouldn't take that to be literally every superluminous supernova should correspond to every FRB, but it's those kind of systems that give...
Even long GRBs also, some of them make black holes. So
yeah.
I fully agree. I'm not saying that they rule out the... I'm just saying probably we should open our mind to some other possibilities as well. Sure. So I think one comment I want to make is about the Maser model. I think this polarization angle sweeping is actually the killer. I don't know whether any of you guys has a way to make the polarization angle change within one burst, because according to Alice's model, I believe it's not magnetized, and Yuri and Lorenz's model, you really need to have very aligned B fields. In this case, you can have coherence. So probably the polarization angle is not supposed to change. And we do see in pulsars, the interaction model is essentially a pulsar model. So back to Dong's question about the duration. In that model, it's just a matter of the location, Lorentz factor, and the sweeping. That would determine the duration, and it can have enough flexibility to do that. But in that picture, we can very easily have this polarization angle sweeping. So I think probably this is the differentiator.
So can I ask within, well, yeah, maybe I'll come back to these points later, but can I ask within your model, what was unclear to me in the neutron star interaction model is, if you want the system to live for decades, you need these neutron stars to be very far apart. And so, I mean, this goes back to John's talk. So, I mean, how do you get enough energy? It seems to me that you just have an energy crisis if you want the system to survive for decades.
You mean the one I haven't you haven't seen yet? Yeah. So you do have enough energy. So the total energy in the lifetime of a magnetar, say, is roughly 10 to the 43 ergs. If you consider each one isotropic energy is 10 to the 39, but you consider like per year you have like say 1,000 of them, and then you consider 100 years. And then you have, in the interaction model, you have a global beaming, so it's not fully isotropic. That probably reduced by a factor 1 order of magnitude. So altogether, total energy is 10 to the 43. It can push it to 10 to 44 if it is isotropic. But just the spin energy of the 2 neutron stars, even the slower ones, is 10 to 45. And the faster ones are even larger. So energy budget-wise, I don't think it's an issue.
Well, I disagree. I mean, we don't have time here to go through the numbers on the blackboard. We don't have a.
There is one actually. It's hiding right here.
The relevant number, as far as I could tell, would be say I have a dipole magnetic field in a relativistic wind. There is a magnetopause, and the relevant energy for some type of spasmodic event would be the dipole energy at the radius of the magnetopause. The dipole energy is dropping off as radius to the -3 from, and if you have 2 well-separated sources, and the wind then is diverging spherically, more or less, and the magnetopause is a long, long way from the dipole.
Again, we are mixing like two of my models. So the direct interaction model is actually very, very close. The orbital separation is 10 to the 9 centimeters, and the time scale towards merge is about decades to a century. So in that configuration, the 2 magnetospheres is actually directly interacting with each other.
What dipole are you assuming a magnetar?
Are you assuming a magnetar, or what sort of field are you assuming this neutron star? That might be the.
No,
Yeah,
it's just.
I'm with Chris on this.
Yeah. It's just the double pulsar situation. So if you.
But it was
So
10
like
to
10
the,
to the
10
12
to the 9 Gauss or 10 to the 15
yeah.
Gauss?
Yeah.
Right. What value? 10 to the 9, 10 to the 12?
10 to 12 Gauss for the
10 to 12, then
for the secondary. Yeah.
So yeah, I don't think that's enough.
Just as an aside question, what is the maximum value people would possibly consider for the magnetic field on a neutron star? 10 to the 18?
10 to the
After
18
that,
in-
just...
But 10 to the 18 is you get into interior structure problems.
So for individual event.
Jim Latter called the Dunkin' Donut.
Yes.
So for the individual event, the energy is actually much less than 10 to the 39. So if you consider it is highly beamed, so it can be as low as say 10 to the 36 or even lower. 10 if the gamma Lorentz factor is say 10 to the 3. So if you multiply the gamma 1 over gamma squared, so individual burst is energy is only 10 to the 33. So it's very.
But you're just talking pure energy budget. You're not really talking about.
So I think this is something we should settle over dinner and a nap.
Beaming also.
Sounds like. So I just wanted to move on. We've talked there. I think one useful thing that maybe we could try to do in the last couple of minutes is to think about whether there are any less obvious observational tests. Obviously, looking for FRBs from superluminous supernovae that happened 10 years ago is interesting. It's already been mentioned that in the neutron star merger models, either whether the merger is, the FRB is contemporaneous with one shot with the merger, or it happens because a magnetar is created in the merger so it lasts for 100 years after, or whether it's happening 10 years before, as we're discussing. Anyway, in a graduate student or at least professor's lifetime, there ought to be a LIGO event at the position of the FRB, so that's obviously one thing to do. We just talked about superluminous supernovae. One thing I thought that might be interesting, we've mentioned a lot of the times the missing energy, that in many of the models there's 10 to the 5, 10 to the 6 times more energy associated with the event creating the FRB. And in some models, there actually are predictions of the contemporaneous optical and X-ray bursts. So I thought, I don't know how many people know about the Tomoe Gaussian CMOS camera, which started operating in full operations a few months ago. So it covers 21 square degrees, which is all they could afford. Not the field is actually, it's basically identical Schmidt to the Palomar Schmidt. They've instrumented 21 square degrees with CMOS cameras, which can integrate down to, which can read at 100th of a second subframe, and the full frame they can do every half second. There's also this conveniently named chocolate hazelnut camera. Nutella in Kazakhstan. George Smoot is building for ultra-fast astronomy, this is 192 megapixels. This one's only, depending on which instrument I think it's not instrumented, but they're exploring 512 and 3600 pixels. Silicon photomultipliers, which would have nanosecond or resolution in the optical. So there are, and these both are pretty wide fields, so I guess one question is whether optical is the way to go, or whether one really needs a giant lobster in the X-ray or something as well.
Yeah.
But
I think this is very important, because I think there are other, as well as these, I think there are other things that are proposed that are out there that are floating around in proposal space, and to sharpen the arguments for FRBs, which could be one of the principal drivers for these facilities. I think through that is important to do at this stage.
It would be great if they could.
Let's see, I think Ailey was
Sorry.
first.
So you're focusing here on very fast cameras, but in principle, you could also live with much longer duration integration, because like 10 to the 46 ergs, even if you spread it over a few seconds, you still quite far.
Yeah, no.
There's a large range in
So I mean, I was just mentioning these because these are new. Of course, one can integrate longer for others.
1 second or minute time response time scales, and here, of course, is out there as well.
Exactly. So this could also do this,
Yeah.
even though it doesn't have such a short.
Yeah. I mean, these are things that are happening, but there's lots of other new things I think that are out there.
You could possibly even use the Cherenkov telescopes. They can image fast in blue light. But they usually have very small fields of view.
Yeah.
If you know the window of repetition, then you look at more pressure.
But I think the problem with those. Yeah, I mean, I think something like Tomoe Gaussian, you could imagine if this circumpolar telescope that was being discussed earlier were just staring at 30 square degrees, and you just point this at the same position, right, and look for coincidences. But yeah, Vicky, did you want to say something?
I was going to say, if somebody wants to build them, could they consider not making those square arrays instead of making long, thin arrays?
No, I think. Well, yeah, that's the telescope problem. I think this is actually, I forget, is 70 Canon camera CMOS detectors pasted together, so they could have put them in a strip. But you need a cylindrical optical telescope, yes. Yeah. Yeah. Right.
Yes, that's been proposed. Liquid mirror telescope.
So, any other proposals for innovative instrumentation? Innovative things that need to be tested?
Okay, can I try in that?
Yeah.
Sorry, in that connection. If the observers, I mean, you might have said that chime was not guaranteed to see something at low frequency because there wasn't obviously a source then, and it's glorious that it has. Why stop there? Is there a sort of a lower frequency space where people ought to be using new
Well, I think so. There have been, I mean, there are limits from MWA and other things. So somebody want to comment on?
Yeah. So, I mean, has this really gone? I mean, has this gone as far as it can go with the, with the things that are built for other purposes?
Not yet, but we're pushing in that direction. So in the Netherlands, we detect FRBs at 1.4 gigahertz with aperitif, and then trigger LOFAR, where we can dump voltage data at a large number of stations and go a lot deeper than the MWA results. So in principle, we'll be able to go down to 100 megahertz in the next several months.
But Liam, that doesn't tell you about the rate of FRBs which occur at 100 megahertz and are not detectable at 1.4.
That's right.
No,
it's not a blind search.
Yeah. What could be done for that?
I mean, a blind search. Yeah, you do a blind search.
Yeah, but which telescope is the best one to do this?
I think it's a computation challenge, right? For LOFAR and other places, you just need to have a lot of beams on the sky. You need to compute a lot of beams on the sky and then search all of them. You could conceivably search like an incoherent beam of all the dipoles together.
So I was actually going to say, I think the sky temperature is a major limitation as well. I'm pretty unconvinced that going down to 100, 200 megahertz is really that much of an advantage. Below about 400 megahertz, you start paying a big price in sensitivity.
It's not crazy. It's not crazy off the plane.
Still, even off the plane, they're talking about system temperature of a few hundred kelvin instead of say 50 or 60 kelvin.
I mean, the thing is, it is somewhat prescriptive. Some of these models are going to concentrate the emission, particularly at a given time, in a maybe in an octave of frequency or something like that. But if you've got it over 10 octaves of frequency, then
Can you please use the hand mic?
Yeah, Ryan.
Yeah, I thought it would be actually interesting to be brave and go to higher frequency, and like build a big path for like a phased array feed for Parkes, which has hundreds of beams, and try to see what you saw there, or Arecibo or something like that.
Yep.
So I think it was mentioned earlier that it would be great to have associated high energy counterparts, maybe neutrinos or TeV photons or something towards it. So another idea I had was you could just build a little tiny radio dish next to IceCube or next to TeV bucket, and you could just sort of swing it. If they detected something, you could kind of swing it to that part of the sky. And because you have this radio delay, because of the propagation through the ISM, you have a little bit of time. So in Uri's original model, he predicted there might be a TeV pulse, and so But since we haven't seen yet any TeV point sources, this is probably not worthwhile doing yet. But you could imagine doing this with IceCube if you had a fast enough readout. You could swing some little dish. Maybe this is impossible. The observers can tell me this is crazy, but.
Or you could just have an array of dipoles.
Or you just have an array of radio array in the ice. I don't know. There's people doing that. Sorry, go ahead. Yeah. I was thinking looking at higher frequencies where you wouldn't, you could have a smaller dish.
Yeah, but there are radio arrays at the low frequencies because that's a way of detecting neutrinos. And
Right. This would be higher frequencies.
Yeah. Right. Yeah.
But why do you want to build a telescope? Like, why not use the existing ones?
Well, you could if you were guaranteed you're at this, you have the right conditions and you could transmit the signal fast.
Today is, but you could probably trigger and get on the source in a minute.
What's the highest frequency one could build chime like?
I think it's the expense of getting the surface good, I guess, is the right.
The computation.
Yeah, and the computations,
It's all scalable. You just lend them.
Money? Well, quadratic money. More than quadratic.
Kendrick might be able to.
Kendrick?
So 2 gigahertz chime, how much does it cost?
10 gigahertz.
Yeah, 2 gigahertz isn't very much. It should go above what we are already doing, right? So 10 gigahertz.
Well, but 10 gigahertz, I like the phased array at Parkes. Seems like the cheap way to go, right? Parkes is detecting bursts.
But bandwidth and the number of beams means that the cost goes cubic.
Right.
Well, it's worth pointing out that not most, 2 of the sort of next generation FRB finders are going to be ultra wideband. So sort of next gen chime chord will be 5 to 1 high frequency low frequency ratio, 300 1500.
So Vikram, DSA 2000, is that going to have millisecond imaging capability?
I mean, anything we want, it's going to have. There's no, just on the surface. I know there's a project in India to build a millimeter chime, much smaller, of course, but there's no issues with the structure and so on. Anyway.
So one of the things which also Chris talked about was CMB surveys, and I'm trying to see get input from others in the community of how we can convince the CMB people that these flashes are important and they should search for these transients. I mean, it's commensal science. We can do it while they're doing their surveys. So the new CMB experiments, if they can set up some sort of instrumentation or anti-coincidence shields for detecting and rejecting cosmic rays independent of what the bolometers see, that would be a very useful thing. But
this might be a good place to talk to the Simons Observatory. Yeah.
Or possibly having 2 telescopes pointing.
Yeah, I mean, there are many CMB experiments which could, if they could be persuaded to look at the same, track each other, I think that would do the coincidence for you, basically.
Everybody talking knows about this. Yes. Of course, they all usually have some pilot project going. Some master student, maybe it's just a matter of, in many cases, prioritizing it.
I think the best way to do it would be to observe simultaneously up to the CMB kilometers.
Please use your microphone. I think the best way to do it would be to simultaneously observe with the CMB telescope at 40 gigahertz and a radio telescope at 1 gigahertz.
But you're not guaranteed that the FRB will be broadband enough that it will be detected in one and not the other. So your limits at best would be sort of statistical.
Oh, well, that's a good point, but I think a blind search with a bolometer-based instrument is just going to be really tough. There are lots of cosmic rays, and the dispersion delays are really tiny, so you can't really use the dispersion sweep to discriminate.
Yeah, so that's what I was saying. Like, if you can put, say, some sort of anti-coincidence detector as people do in X-ray telescopes to detect the cosmic ray independent of the bolometer.
But I think the other approach would be if you just convince 3 different CMB experiments to track the same field. That would, you'd have a geometric separation as well. Yeah, Vikram.
Is it bad to ask about emission mechanism?
I think the emission is supposed to be tomorrow, right? Is that
or
right?
engine, or like the scenario, basically.
Yeah, scenarios are fine.
Yeah, I'm just curious what people think about the Mottes and Zarka model given the 16-day periodicity. There the idea is there is a neutron star and there's a planet or whatever orbiting it. And so there are 2 alpine wings. And the emission happens because of a major instability in the alpine wing. In the same way Io and Jupiter work, basically.
I think similar comments might apply to Bing's approaches, but I have to take a look at the paper.
Yeah, I mean, the decametric radiation from Jupiter is a real thing, and it's coherent, but it's not on the scale of an FRB, for which we should be grateful.
No, it's not. That's why. That's why you replace Jupiter with a pulsar, basically.
Yeah, I think that energetically it's not enough.
Okay.
By many order of magnitude, if you do a simple calculation, you've done many times, people repeatedly doing these things, basically. Try to use unipolar inductor at large distance is very inefficient, I think. I used to think it's easy to do now, but once you revisit this thing,
No, it's a real thing. It's just that the physics of the interaction with Io turned out to be more complicated.
Yeah. And then Tony is here. You were trying to do the calculation, real thing, right? I mean, you can comment on the thing. It's very small.
Depends how strong you make magnetic field.
Of course.
Yeah.
Of course.
Yes.
But 10 to 14 is not enough either.
So I think the bosses are saying we should continue this over dinner. Is that correct?
This is all very interesting. Let's thank our panelists.